Let's do now a more interesting example, which is the impulse train. Xt is defined as summation define the summation over k from minus infinity to plus infinity, delta impulse, a unit impulse function, t minus k some t, let's say t now. So this signal is just a collection of impulses, or what we call an impulse train. And if you plotted t, it's just unit impulses at all integers of t naught. So first, when k equals 0, we have this impulse. Let me use a different color. And then at t naught and minus t naught, and at 2t naught minus 2t naught, and so on. This 0 t naught, 2t naught, minus t naught, minus 2t naught, and so on. And we need to find the Fourier transform of this signal. Notice that this signal is periodic. This signal is periodic, so we can find its frequency representation or frequency series representation using what we have learned before, using the Fourier series. First, we find the coefficients, and then we can write it in terms of Fourier series. And we will benefit from that here to find its Fourier transform. And that's why this example is interesting, because it will show you the relation between Fourier series and the Fourier transform. First, let's find its period. So the period, or the fundamental period, of xt is t naught, and then its fundamental frequency, or the corresponding frequency for this period, will be 2 pi over t naught. Okay. And also we can write in terms of the frequency in hertz, f naught is just 1 divided by t naught. Now remember from Fourier series, xt can be represented using a Fourier series this way: k equals minus infinity plus infinity, some coefficient, and then scaling the harmonics, jk omega naught t. And then those coefficients can be found using this equation: 1 divided by t naught integrating over one period, and then xt exponential minus j k omega naught t dt. And the integral can be done over just one period, so or it should be done over just one period, so we can do it this way from half the period to half the period, from minus half to 1/2 of the period, and then xt exponential minus j k omega naught t. And if we look at this interval from minus t naught over 2 to t naught over 2, so it's from somewhere here to here. And this period contains only just one impulse, which is delta at t, delta of t. So this is just delta t. And this one is delta t minus t naught. This delta t minus 2t naught, and so on. But within this interval, we only have this impulse. So xt over this interval is just delta t. So because we are within this interval, we can rewrite this as 1 divided by t naught minus t naught over 2, t naught over 2. And then xt over this interval is just one impulse. And dt here. Now we will use a very important property of the impulse, which is the shifting property. Which says when we have some integral from minus infinity to plus infinity, or from some negative to some positive numbers around this impulse, and then times some function, the result will be just this function evaluated at 0 in this case. And to make it more general, we can write this delta t minus t naught. So we have a shifted impulse times ft dt. This will be f at t naught. So using this shifting property, we can simplify this integral, and it will simply becomes 1 over t. And then using the shifting property, this will be exponential minus j k omega naught times 0, which is 1. So 1 over t. So ak is 1 over t. So all of the coefficients will have the same length, and they will all have the same amplitude, which is 1 divided by t. So if we write xt in terms of Fourier series, we'll have this xt equals summation minus infinity to plus infinity, this t naught, 1 over t naught exponential j k omega naught t. Okay. Now we have just changed the representation of xt, or rewritten xt as a Fourier series. Now we'll use the properties of the Fourier transform to find the Fourier transform of this signal, because now it's represented in a much simpler form. If we compare it with this form, which is a summation of shifted impulses, now we have exponential, and exponentials are easier to deal with in Fourier transform or Fourier series. Now, if we want to take the Fourier transform of this signal, so xt will do a Fourier transform. We'll get let me write this. Let me write it this way to be clear. So if we apply Fourier transform over this signal, it will be as if applying the Fourier transform over this summation. Okay, but Fourier transform is a linear transformation. It's a linear transformation. So we can rewrite this as we can take this one over T naught outside, so and the summation also. We can take the summation outside the Fourier transform operation because the Fourier transform is linear, and we can do just the Fourier transform of this. Now we have a very simple or much simpler form of a function to do a Fourier transform for. And here we just have to find the Fourier transform of this simple exponential. And if you go back to the main lecture, you have found the Fourier transform for this, which was this way. If you take Fourier transform of this, you will have 2 pi delta omega minus k omega naught. This is from the main lecture. Main lectures. And we're done. We'll just substitute this here, and we have found the Fourier transform of the impulse train. Therefore, the Fourier transform of the given signal xt, which we call x j omega, is 1 over T naught summation k from minus infinity to plus infinity. And then the Fourier transform of this exponential, which is 2 pi delta omega minus k omega naught. We take this 2 pi outside, and then we'll have 2 pi divided by T naught summation k is minus infinity to plus infinity. Then delta omega minus k omega naught. We can write this as omega naught, because omega naught equals 2 pi divided by T naught. Let me write it also this way. So omega naught summation delta omega minus k omega naught. K from minus infinity to plus infinity. And if we plot this one, omega and x j omega, it will look like also a train of impulses. And they are scaled by omega naught. So omega naught omega naught and so on. So the Fourier transform of the impulse train is also an impulse train, but the scaling is different. In this case here we have the scaling was just 1. The impulses are scaled by 1, and the spacing between the impulses is T naught. When we move to frequency domain, the spacing between the impulses is omega naught, is the fundamental frequency of the signal. And I think that will be all for today. Thanks for joining and for watching the workshop. See you next time.